Okay then, today's a culmination of the last 2 weeks lectures where we've been looking at gear trains, analysing velocity ratios, input and output speed and so on. And it's all been leading up to this moment when we start looking at epicyclic gear trains. And I have to say they're not for the faint-hearted, epicyclic gear trains. I take my hat off to people that design epicyclic gear trains. They are really quite complicated bits of kit. So what you're seeing in front of you is an epicyclic gear train. It's actually a single stage gear train. This one up here is a single stage gear train. We will be looking at slightly more complicated ones, and we're going to start with those. And they really are quite difficult to visualize. You'll see today we'll adopt a very standard sort of tabular approach to trying to calculate the velocity ratios of these epicyclic gear trains. So although initially it might seem very complicated trying to understand the rotations, relative rotations and so on, what we'll end up with is a fairly reasonable tabular approach that we'll use for every question, where we'll try and break down the individual velocity ratios within the epicyclic gear train, and from that we can generate equations and then solve for various speeds. But they certainly are quite complicated pieces of equipment. So this is showing you a single stage epicyclic gear train. It's like the three-dimensional view above here, when we've got what's called a link arm here, and it's driving a planet gear that drives around the sun gear, which is the middle gear, and it's all within the annulus, the sort of frame, if you like, the internal teeth we mentioned last week. So those are typical characteristics of the epicyclic: the sort of sun gear in the middle, planets evolve around the sun, strapped to a link arm or a planet carrier, and then they all evolve around the annulus. And of course we've got our driven and driver input and outputs, as we would normally have from a gearbox. This is a two-stage epicyclic here, so slightly more complicated here, but same principle. We've still got sort of an input shaft driving this sun gear, which drives planet gears, which drives the annulus. They all interlock between them, and in this case we've got a second stage epicyclic gear train to consider, so to get our output. So quite complicated configurations we're going to look at here. Okay, so that's what it's all about today, trying to bring in all the knowledge we've accumulated over the last two lectures, and we're going to apply that here in a more complicated context. So again, just looking at the basic elements, this is again a single stage epicyclic, clearer to see perhaps here. We've got an annulus that's fixed here, so the annulus, which is the this outer red ring here, it's called the annulus. That's fixed in this particular case. And what you'll find in the analysis that certain gears can be fixed in epicyclics. That's how you get the different gear ratios. Sometimes the annulus might be fixed, sometimes the sun might be fixed, sometimes the link arms are fixed. You can fix different aspects of the epicyclic gear train, and that will generate different velocity ratios for you. So in this particular scenario, they're showing these big lugs here, so they're saying, well, we're going to clamp down the annulus, and everything is running around the annulus here, but you've still got the same kind of characteristics here. We've got the sun wheel in the middle here, we've got the planet gears going around, these four of them shown here, going around the sun here, and this thing here called the cage, sometimes it's called a spider, sometimes it's called link arms, that's what holds the planets in position as they run around the sun here, and they're all running around this internal tooth annulus here. Okay, so those are the basic sort of configurations that we've got in this case. If you look at these sort of sensors, and again the sensors of which sensors the gears are going clockwise or anti-clockwise can be quite difficult to visualize with epicyclics. So you'll see later on we will let the mathematics this time decide the overall directions of the gears. But in this example here, what we've got is the cage, or the link arm, is rotating in a clockwise direction. So this is the cage or link arm going a clockwise direction. Then the planet gears, that's these here, these are planet gears, then they would move in an anti-clockwise direction, if you can visualize that. This spider arm is going in a clockwise direction. So if you think of the movement of the planet gears with the annulus fixed, they would go in an anti-clockwise direction. Or the sun in this case would go in a clockwise direction, because it would be opposite to the planet gears. So just that little illustration there, because it's quite complicated to think what's going on here. This spider, this cage, this link arm is going in this sense here, then this gear wheel will go in this sense here, okay, which will move the sun in this sense again. So that's what I'm trying to show there. So the basic relationships we have between our simple gear trains and our compound gear trains that we've looked at over the last few weeks, that's still applicable here. It really underpins Epicyclic. So if you don't understand how compound gear trains, simple gear trains work, then you can't analyse Epicyclic. So everything we've done over the last few weeks is kind of can be brought together here in what we're going to look at here. This example, of course, shows that the input and output rotate in the same direction, but of course that does depend on the configuration of the Epicyclic, whether that's true or not. Okay, so where do we use these Epicyclic gear arrangements? Well, primarily in automatic gearboxes or complex steering mechanisms. They can be used in automobile applications. Is one of the main areas where we use these kind of arrangements. And I was also told recently that they're also used in hub reduction gears and auxiliary gearboxes of heavy goods vehicles. I'm not come across that myself, but somebody mentioned that to me recently in other illustrations where they use. So automobile kind of gearboxes is where they're predominantly used. I found this is a very complicated illustration. It's trying to show you how things work here. And this actually has clutches involved here. There are actually clutches here. There's two clutches. There's a clutch here, and there's also another clutch shown here. It complicates things still further. Don't worry, you're not going to have clutches to deal with in your scenarios, but this is just a scenario I found here. And what they're trying to show you with this scenario is how you can fix different parts of the Epicyclic gear arrangement and then change the velocity ratio. So they've also got what they call brake bands here. There's a brake band, if I can highlight it, it's a brake band shown down here. Okay, and there's a brake band shown over here as well. And these can actually clamp the outsides of the gearboxes, and again they can change the ratios or even change the direction of the output shaft to the input shaft by bringing in these brake band belts to stop the Epicyclics. So they're very complicated arrangements, and to try and figure out what the velocity ratios are, and this is not an easy exercise. So you'll be pleased that we've got it down to a reasonably standard approach in our table. Just looking at one illustration here, they've got all the different gears highlighted, but in gear 1, for example, they've got the clutch 1, which is this clutch here, that's unlocked, so that clutch is not working, but they've got clutch 2 here locked, and they've got the band here. The first band is not in operation, but the second band is in operation. And if you look at the configuration here, what happens here is the input shaft drives the first annulus, so the first annulus is driven here because this clutch is locked here. Then the input shaft, this dart shaft, is then clamped to the first annulus by this arrangement here. Okay, so it's clamped to the first annulus, and that first annulus drives the planet wheels, and then that drives the planet carrier, and the planet carrier drives what's called the output shaft. That's the output shaft shown there. So that's like one approach through the Epicyclic gearbox. That gives you what they call gear 1. And they just change things when they want different gears. They just change the configuration. So in the next configuration, they've still got clutch 1 unlocked and clutch 2 locked, but now they bring in one of the bands here to stop the rotation of the outside of the Epicyclic here. And that will actually change the velocity ratio of the gears. Although the actual configuration is the same, it's still sort of driving the first annulus, it's driving the planet gears and the output carrier. Because the outside here is constrained, it's now stationary, it will then change the velocity ratio of the output gear, and so the output shaft. And they just all play tunes on this as a third gear they show, which is where they lock both clutches up, so the input is actually driving directly on the output here. And then on the reverse gear, they actually bring in this band here, 2 comes into play, and that then reverses the direction, so you get a reverse gear. So there's lots of different variations you can have with Epicyclics of holding certain gears, freeing certain gears, and it changes the velocity ratio of the gearbox. So they're very, very clever bits of kit, these. I really do take my hat off to people that are designing these Epicyclic gear trains. You'll please see ours are a little bit simpler than that one we're going to look at. There'll be no clutches or no bands involved with us, but we will have fixed gears, and the questions will say if the gears are fixed, they will tell you which gears are fixed, and then you have to work out the velocity ratio around that configuration. So I'm just trying to show you with those slides that there's various configurations you can get by holding the annulus or freeing the annulus, holding the sun gear, freeing the sun gear, and so on. So lots of configurations we can have here. Just looking at recap what we've done the last few weeks, all these relationships on the slide now, or if you look in your revision booklet, you'll find them all in your formula booklet. And they're all going to be with us today, okay? So we're not forgetting what we've done over the last few weeks. In fact, the last few weeks we're really building up to this moment in time here. So we will still have today simple trains to consider in our analysis. So the velocity ratio of a simple gear train, the G, if you like, which is the speed of the input gear over speed of the output gear, is the number of teeth of the output gear over number of teeth of the input gear, or diameter of the output gear over diameter of the input gear. That's still applicable today. And of course, our compound gear trains had this formula for G was the product of the number of teeth on the driven gears over the product number of teeth on the driving gears. Again, that's something we're going to use. So we'll be using relationships shown here. This velocity ratio for this particular gearbox is shown here. We'll be using those kind of relationships within the epicyclics. Also, there'll be geometrical considerations. In some of the questions, we will not have all the number of teeth we need, so we need to look at geometrical considerations. So again, going back to what we looked at in previous work, you've got a shaft like this where we know a distance between the centres of the gears. This is what's called a coaxially mounted compound gear train. Then this relationship is true. The diameter of gear A added to the diameter of gear B on the left hand side must be equal to the diameter of gear C added to the diameter of gear D on the right hand side. They're actually talking really in terms of radii, but we can equate that to diameters. And then of course we've got our relationship then in terms of number of teeth. We can write the D's, if you like, in terms of the ends for the number of teeth. So again, that relationship will be used in some questions. And this final relationship, which relates to the module. If we've got connecting gears, A and B are connecting, so they must have the same module. C and D are connecting, so they must have the same module. In that case, we can write another equation for geometrical constraints, but this time it's in terms of number of teeth on the module. And don't forget the diameter of a gear, or the pitch circle diameter, is the module times the number of teeth. So all those relationships are with us today in what we're going to do. So an alternative method of obtaining concentric motion of an input and output shafts is to use epicyclic gear trains. Now the design provides high gear ratios within a very small volume. I think you can see that from the previous slide. In a fairly small volume of the epicyclic gear train, we can have considerably different velocity ratios for our gearbox. So very useful from that point of view. And of course, that fits nicely in things like car gearboxes and so on. So that leads to saving in weight, of course. So that's one of the advantages of them. They're fairly condensed in their space requirements, and of course they're lighter because of that. It also has the capacity of giving a change of velocity ratio by locking or freeing a member of the gear train. Now, epicyclic gear trains, they always include a sun gear, shown here in this little diagram here, sun gear, planet carrier there. That's the link arm, effectively. There, often called the link arm, which is this spider type diagram. And they have one or more planet gears. Okay, and the planet gears are these things up here. So there's one there, two there, three there. Okay, so in three they can have more than that. Often a ring is included, which has internal gear teeth, and that meshes with the planet gear teeth, and that's known as the annulus. So this is the annulus here. This okay, this is on the diagram there. Okay, so that's the kind of configuration we'll have in every gear train. I'm just looking at there what's called a single stage epicyclic. We can get multiple stage epicyclics as shown in the previous illustrations, but we're going to start off with looking at single stage epicyclics to begin with. And again, you can see on the right hand side diagram there's the link arm again that attaches to the planets. Okay, and then the planets evolve around the sun. Here's the sun. I've got the output shaft there. Okay. Alright, so that's the basic configuration of an epicyclic gear train. So simple and compound gear trains, they have what's classified as 1 degree of freedom, in that for a given input speed, the geometry of the gear train is such that there can only be one output speed. And that's the kind of gear trains we've been looking at over the last 2 lectures. Unfortunately, with epicyclic gear trains, with the introduction of the planets and their bearing arms, their link arms, this introduces what's called an extra degree of freedom. So for a given speed of one part of the epicyclic gear train, it's no longer possible to solve for the other speeds. In sort of mathematical terms, you need more simultaneous equations to solve for all the various speeds of the gears. So epicyclics are actually described as 2 degrees of freedom, which means that for a constrained motion, any 2 of the elements, so the planet, the sun, the annulus, the link arm, etc., in the train can provide an input. And again, you'll see this later on. So to solve for an epicyclic problem, we need 2 speeds given to us before we can find the output speed. So they're just more difficult to analyse, more complicated because they've got more variables. If you think back to all what we've done so far, when you think about the gears spinning, they were spinning on shafts that were stationary. Now you've got a situation where gears are spinning on shafts that are actually rotating in a circle themselves, or they could be rotating. So you can see there's a slight complication there that we haven't had before in the previous exercises we looked at, and that's where the kind of 2 degrees of freedom starts to come into play here. So again, looking at a notation for epicyclic gear trains, they call them simply epicyclic train here, but they're not terrifically simple really. But anyway, in a simple epicyclic gear train, we have the A, which is the annulus wheel. That has internal teeth. We mentioned these last week in the second lecture about having internal teeth and the effect on the direction of a gear run on internal teeth. So we'll be seeing that effect later on. So the annulus is A. That's this ring here. I've got the colours again. Okay, we have the P for the planet wheel, and the planet wheel's P there. That's these 3 wheels shown here. And we have what I've called the link arm here. It's got different names. There's so many different names here. So I normally call it a link arm, but it's also called a star. It's called a spider. It's called a cage, depending on which books you look at in your analysis. And the link arm is shown in the sideways sketch here. That's the link arm that connects the planets. So this triangle shape here is sort of showing the link arm effectively. And then we have the sun wheel, which is the center wheel here. That will be the sun wheel right in the middle there. Sun gear we've got here. So just think of this carefully. We've got the planets P. They mesh externally with the sun wheel S, okay, and they mesh internally with the annulus A, so just be careful of that. And the input and output shafts may be connected to any 2 of the sun, the annulus, or the link arm. So you can see we've got quite an array of different configurations that we're going to we could come across in the analysis of these epicyclic gear trains. So lots and lots of variables here that makes them much more difficult to analyse. So solution of the epicyclic gear problem is one of relative motion, and that's the bit to me that makes it quite complicated, trying to think of the relative motion. If you ever look at the theory behind what we're doing now, it's quite difficult to comprehend the theory. At least I find it quite complicated theory here, what it's based on. It's very clever theory, but it's all based around relative motion. So we're going to keep it as simple as we can using this tabular method to try and determine the relative motion. And you'll find there are 3 distinctive steps we will apply in the table, although it does depend on whether we've got a situation where all the gears are free to rotate, or a situation where a gear is locked. So there are 2 types of scenario that we can use for our table, you'll see in a moment. So by using the either the algebraic approach or our tabular approach, we're going to generate simultaneous equations. In some cases they'll be very simple, very straightforward to solve. Other cases just might want a little bit of manipulation. Again, it depends on the configuration we're looking at. So we can use these simultaneous equations to solve for the unknown gear speeds. So relative motion between a pair of mating gear wheels is always the same, okay, whether rotating or not. But one thing we haven't had before, as I said previously, we haven't had a situation where the spindles that the gears are connected to are moving. They've always been fixed in all our simple trains and our compound trains. Now the spindles are moving. So now we have to be careful. We have to make sure we always have our velocity ratios, our gear ratios related to the link arm. And this is really important. You must remember this. So it's very important to generate your equations. They must be relative to the link arm always. In other words, we're considering the link arms to be fixed, if you like, as far as the gears that hold them are concerned, which would be the situation you'd have if you were looking at a simple or compound gear train you had in the past. So we're kind of doing what we did before with the previous analysis when we're undertaking our calculation of velocity ratios, but we've got to be careful here because the link arms they're connected to could be moving. So it's important to always generate equations relative to the link arm of the respective epicyclic stage you're considering. Let's consider this single stage epicyclic gear train. I'm just showing you here a sort of diagrammatic view. I've got my sun here. I've got my link arm that's connected to the planets, to the sun. I've got my annulus or ring gear, it's sometimes called, and I'm just showing a gear outside of that as well. I'm just trying to show you this because I want to get the directions clear in your mind. Just recapping really what we touched on last week about having internal teeth and the effect on rotations. So equations of a single stage epicyclic gear train are shown below, okay? Now, within this work, I am going to put the sensors in. In all the previous work, when we are asked to find out what's the direction of the output shaft compared to the input shaft, we just use velocity arrows, because it's very, very straightforward, really, with our simple and compound gear trains to work out the direction of the output shaft relative to the input shaft using the velocity arrows. Now it's not so simple with the epicyclic gear train. So now I'm actually going to include the directions of the gears within the analysis. So if we consider here gears A for the annulus and S for the sun relative to the link arm, if we were writing this down academically, we would have to write it as the speed of the annulus, speed of gear A, minus the speed of the link arm divided by the speed of the sun. In this case, take away the speed of the link arm because it's relative to the link arm. Now, what we are going to do in the analysis in a moment to sort of simplify this for ourselves, we're going to make sure that the link arm speed is always zero, and this is what the tabular approach helps us with. And then again, notice our relationship here. We've got the inverse here. Notice this is the number of teeth on the sun gear divided by number of teeth on the annulus. It's upside down, aren't they? Back to our relationships of the speeds, number of teeth, remember. But what I have put here, I've put the negative value on the right hand side here to show that if we're considering the sun and the annulus, they will actually go in different directions. So again, let's just think that through for a moment, just so we're clear on that. If I say that the sun is going, in this case, in an anti-clockwise direction, as it's shown here, then my planet will go in a clockwise direction. And that means because I'm contacting then the planet to the internal teeth, don't forget that goes in the same direction, in this case, as the planet. So that will go in a clockwise direction. So the sun and the annulus here, they go in opposite senses, and that's why that negative is shown on the right hand side of the velocity ratio there. So the last line, which is when you're interested, this line here, back to our standard relationship of the speed of the gear A over the speed of gear S is equal to the number of teeth on gear S over the number of teeth on gear A. We're used to those inverse relationships, but I have that negative sign now to account for the change in direction. This is really considering the same train, same gear configuration in figure 3. This time I'm considering gear P and gear A, so planet and the annulus here, again relative to the link arm. So again, if I assume that the link arm is going to be 0, I can simplify the expression to the speed of the planet over the speed of the annulus is equal to the number of teeth on the annulus divided by the number of teeth on the planet. Notice I've left it as positive here because the planet and the annulus, they will go in the same direction, so they're a positive direction. But we do need to put the negative in where it's applicable in our gear train. As I say, slightly more complicated analysis to consider. Let's look at the two conditions that we're going to come across in this work. So I'm going to use a set of tabular approach here to help us in the solutions. So the first condition, first general condition it's called here, this is where all the gears in our epicyclic are free to rotate. Nothing's being clamped in this case. And then the more complicated ones to analyse because effectively they've got more unknowns. So this is a configuration on the right hand side that we're looking at. We've got sun, our planet, our link arm and our internal gear wheel, the annulus. They're all free to rotate in this particular situation. So if you have a situation where nothing is clamped, all gears are free to rotate, this is the way the tabular approach will work. And this is our three-step process we're going to use. In the first step, we imagine that the whole assembly shown at the top of the slide here is going to be locked. It's all fixed. And we rotate the entire gear train through what's called plus m revolutions. So because they're all locked and we're rotating it, say, through 10 revolutions, then everything effectively, our link arm, our annulus, our planet, and our sun, they all rotate positive m. Okay, we don't know what m is, we're going to find it. M is an unknown. In the second stage, we're going to fix the link arm. As we said, we must always generate our velocity ratios relative to the link arm. So we're going to fix the link arm here. And what I'm going to do here is rotate the annulus, the outside member here. I'm going to rotate it positive n revolutions. Any gear can be chosen, just using the annulus here for this example. So in the second stage, let's try and think this through what's going on here. For the link arm, we're having the link arm is fixed. So for this second line of our table, it won't rotate. Okay, it is fixed in this case because we're generating our gear ratios relative to it. So we're assuming it to be fixed. We're saying over here we're going to apply positive n revolutions to the annulus. We chose the annulus to rotate. Positive n revolutions. So now we've got to think of the gear train for the speed of p when we've got the annulus rotated n revs and we've got the link arm fixed. So what you're seeing in this box here is actually the simple gear train for the situation of the planet contacting the annulus. Okay, so on the other page, let's just highlight this here. So this line here is simply this gear ratio. So the speed of the planet over the speed of the annulus, I'm trying to find the speed of the planet here, is the number of teeth on the annulus divided by the number of teeth on the planet. That's what I'm using. That's a simple gear train, going back to what we did in week 1, effectively. A simple gear train of the annulus connected with the planet. Okay, so that's what I've written there. And all I've done is transposing. I'm trying to find what the speed of P is, so I'm multiplying both sides here by the speed of gear A, and we know that the speed of gear A, the annulus, is positive n revs. So that's where the positive n revs is multiplying the number of teeth on the annulus divided by the number of teeth on the planet. Notice, we've got to this slide, notice that I've got a positive here, there's no negative because the annulus and the planet, because they're connecting, you've got an external tooth gear planet with the internal tooth, the annulus, they will go in the same direction. So there's no need for a change of sign between the annulus and the planet. They go in the same sense, okay? So if the annulus is going positive n, the planet goes positive n effectively, all right? And in the last cell here on the second row, I'm now considering the speed of the sun relative to the speed of the annulus. And again, this expression here is really, if I go to this slide, it's just showing you I've got the speed of the sun over the speed of the annulus is the number of teeth on the annulus divided by the number of teeth on the sun. Okay. Now in this particular case, I do need to add in the negative value because the annulus and the sun will go in different directions. You can see here the annulus is going in a clockwise direction shown up here, then the sun is going in an anti-clockwise direction here. So I do need this negative value now to put into my gear ratio because I'm accounting for the directions in the equations. So I've got negative A upon the positive NS there to try and show the directions of the gears are different. So that's where the negative n comes from, but it's multiplied by the number of teeth on the annulus to the number of teeth on the sun. So that centre section is where we will have, these are simple gear trains. Unfortunately, we will have also compound gear trains to consider, but that's basically the prerequisite work we looked at in the previous lectures of how to apply these simple train and the compound gear train velocity ratios. That's what will be in the second row. The third row is the easy one. It just simply adds up the first and second rows. So if I take my speed of the link arm, initially it was plus m, then we fixed it. So when I add the two up together, I'll get just plus m. That's where that comes from. So I'm just literally adding up my column here. For the annulus, we had a plus n to begin with. We had a plus n because we rotated it in positive n. So the m plus n is the summation of the speed of the annulus column, summating the speed of the planet column. We've got m from the first row, and then we've got the added to that the n multiplied by the number of teeth on gear A divided by the number of teeth on gear P. And then similarly for the final one, we've got the m, but this time it's take away the n times number of teeth on gear A divided by the number of teeth on gear S. So we've got some equations there. So we would have to be given more information about the gear train. We need to know two velocities given to us, but then we could use those relationships to find the velocity relationships between the various gears on the epicyclic gear train. I'm going to show you later on some illustrations of how this works. That's a generic process involved, and that's a situation where you have all the gears that are free to rotate. And the questions dictate this. They will say all gears free to rotate, or they will say annulus fixed, sun fixed. They will tell you if a gear is fixed. If we do have a situation where a specific gear is fixed, and I said the questions will tell you that, so the wheel speed of that gear will be 0. Now we have the same kind of approach here. It's just a slightly simplified approach to working out the velocity ratios, because we need less information than if they're all free to rotate. So we're going to have the same table, same kind of structure here. Again, it's the same sort of procedure. We're assuming that the whole assembly is locked and rotating the whole gear train revolution. We're just using it as +1 revolutions here. So everything in that first line gets a +1. We're not using the plus m notation. And that's because we have less unknowns. When we have a fixed component in our gear train, we actually have less unknowns. Okay, so this time we'll do +1 across the first row there. So we're fixed. Imagine you're fixing everything. You're just turning everything to 1 revolution. So everything moves 1 revolution. In our second stage, it's very similar to what we did in the previous analysis. We're going to fix the link arm, because we always must have our velocity ratios relative to the link arm. So you'll see the link arm has got 0 there. It's going to be fixed. And we're going to rotate the annulus. In this case, we're going to rotate it -1 revs. Okay. So if the annulus rotates -1, then I put -1 in the column for the annulus. And then I have to go back and think of my relationships here between the annulus and the planet. So this column here is trying to find the speed of the planet. So no difference here. If I just highlighted this for you again. So this row here, this element here, is simply the speed of the planet divided by the speed of the annulus equals the number of teeth on the annulus divided by the number of teeth on the planet. Just rearrange it to find the speed of the planet. So multiplying both sides by the speed of the annulus. Okay, so that's what's going on in that cell. So that's what I've got there. So that -1 is actually the speed of the annulus, and that's multiplied by the number of teeth on the annulus divided by the number of teeth on the planet in this case. Again, if you look at the senses here, the direction of the annulus and the direction of the planet are the same. So that -1 you're seeing there, that's actually from the -1 we've rotated the annulus at. Okay, it's not due to the senses. But in the next box, it is due to the senses, because what we've got now here is the relationship between the speed of the sun and the speed of the annulus. So again, from my simple gear train here, the speed of the sun will equal the speed of the annulus multiplied by the number of teeth on the annulus divided by the number of teeth on the sun. But I have put now a negative in here. That negative is accounting for the direction, because the sun and the annulus go in different directions. As we said before, the sun is going anti-clockwise and the annulus is going clockwise. So that's why that negative is now in the calculation. And of course, 2 negatives here will then make a positive here. Okay, but the last row is just a question adding up the columns. So 1 plus 0 is 1, and 1 take away 1 is 0, which is correct, of course, because if the annulus is fixed, it cannot be rotating. So that's correct. We rotated the annulus -1 for that reason. And adding up the speed P column is 1 minus the NA divided by the NP, and then add in the final column, it's 1, and then it's plus the NA divided by the NS. And again, from that, we can find velocity ratios between the various gears, the planets and the annulus, the annulus and the sun, etc., whatever we need to find. Okay, so that's the generic processes involved, and there are two conditions, a general condition and a specific condition. But let's just talk this through. This is example 1. We've got an epicyclic gear train that's shown in the sketch. Now it has a fixed annulus, so straight away I'll be using the technique here, this kind of approach here. If it's got a fixed annulus, that's the approach we're going to use. And it's got 100 teeth on the annulus, and the sun wheel has 40 teeth. All right, so this is the sun wheel here, and then our annulus is this thing up here. That's this outside thing here. Okay, that's the annulus effectively there. So part A is determine the number of teeth on the planet gear. So obviously I'm giving us all the information, so we need to look at the geometrical constraints in a moment. We've got to calculate the gear ratio between the sun and the link arm. As part C, we've got to calculate the gear ratio between the annulus and the link arm if the sun is now fixed. So we've got a different configuration for part C there. So we'll look at that separately later on. All right, so 3 parts to the question here. The first part is to do with looking at geometrical constraints, because we need to find the number of teeth on the planet gear. It's not given to us. All right, so taking information from the question, as always, be very careful with the information. We've got the number of teeth on the annulus is given to us. We've got the number of teeth on the sun gear is given to us, and we know that the annulus is actually fixed here. So it's a fixed outer ring. Looking at geometry, let's see if we can think this through on our geometrical constraints here. We're trying to find the number of teeth on the planet. We don't know what it is. So in part A, can you see this constraint here? The diameter of gear S, which is the sun gear, added to twice the diameter of the planets is equal to the diameter of the annulus. And don't forget, when we're talking diameters, we're always talking pitch line diameters, going back to what we looked at in a previous lecture here. So we're talking pitch line, the contact lines between the gears here. So let's just think that through for a moment, make sure we clearly understand that. If I sort of sketch on this diagram, we've got the diameter of the sun wheel, so that's the diameter S that they label below, so diameter S. And then we've got the twice the diameter of the planet. So what they're getting at there is we've got a planet diameter here, and of course we've got a planet diameter here. So that's my D planet, and of course there's 2 of them. So adding the diameter of the sun wheel to the twice the diameters of the planets, that actually gives us the pitch circle diameter of the annulus. Okay, that would be that point there is what we're adding to. Okay, so that's just from the geometry, looking at the constraints we're given for the gears here. Now again, I'm just sort of showing this I'll just show this once and not again. For reference, we already know this really, but I'm just going to labour this a minute here. Because all these gears are connecting, they must have the same pitch, and therefore they must have the same module. So the module between each of the gears must be the same. You know, the module is the diameter divided by the number of teeth from our previous work, so we can rearrange that. The diameter is equal to the module multiplied by the number of teeth. We've seen these relationships before. So equation 1 above could be written in this format of the module times the number of teeth on the sun gear added to the twice the module times the number of teeth on the planet gear is equal to the module times the number of teeth on the annulus. And of course the modules have to be the same, so we can basically write that as number of teeth, and that's what's shown below here. The number of teeth on the sun wheel added to twice the number of teeth on the planet must equal the number of teeth on the annulus. Okay, we kind of know that relationship. We understand that diameters, number of teeth are basically the same. As long as the gears are contacting, that will be true. So I can just write it in terms of number of teeth. And of course I have the number of teeth on the sun wheel, I have the number of teeth on the annulus, so I can rearrange the equation. So my NP here, just rearranging the equation, I would just subtract NS from both sides and then divide by 2. And I get half of NA minus NS is the equation. So putting my numbers in for the gear wheels, that will give me 30 teeth on the planet. So that's like a geometrical constraint there, and that crops up in some of the questions. We need to find the number of teeth, because without number of teeth we won't be able to find the velocity ratios. Okay, so that relationship, that sort of D relationship in equation 1, we'll see that kind of thing crop up in other questions. So example 1 continued here. I just repeated here the number of teeth on the annulus, number of teeth on the sun wheel, number of teeth on the planet. We're going to follow our 3-step through here because this is a situation where we have a fixed gear, the annulus is fixed in this case, then I'm going to use the process where I'm going to apply a positive 1 rotation to all the gears rather than the positive n notation that we would use if no gear was locked. So a slightly simplified approach we can have here in this case, and that's because the annulus is fixed in this case. So that's important to note that. Well, that's quite critical to the analysis here. Okay, so step 1, we're going to apply a positive 1 rotation to the locked gear train. We assume everything's locked and it's 1 revolution about the main axis, so everything moves 1 rev. Now in this particular case, we're going to assume that the link arm is fixed here. So that's where the 0 comes from, and then the annulus is going to have a negative 1 revolution because that's the gear that's actually fixed in the assembly. And then the next little box is then working out the relationships between the speed of the gear P, the planet gear, and the speed of the annulus. So we know it's the number of teeth on the annulus divided the number of teeth on the planet from our previous work. And then we're multiplying that by the speed of the annulus, which is negative 1 in this case. So putting our number of teeth, which is from the left-hand side, number of teeth on the annulus is 100, it says. Number of teeth on the planet is 30, so we can work that out to give us the gear ratio of 3.33. It's negative because, of course, the rotation is negative. For annulus, it's negative 1. And then on the last box, we're taking into consideration the speed of the sun compared to the speed of the annulus. So again, our number of teeth now on the annulus divided by number of teeth on the sun. But of course, the sun and the annulus will go in opposite senses, we mentioned previously. So that's why that negative is introduced there in the bracket. All right? It's negative because the annulus and the sun go in different directions. We have a negative 1 here because that negative 1 is to do the speed of the annulus. So we've got double negatives there, makes a positive. And again, inserting a number of teeth, it's 100 on the annulus, 40 on the sun wheel. So that gives a ratio of a value of 2.5 there. What we do in the last one is simply add them up. Just add up the columns. So the link arm added 1 to 0. It gives us plus 1 for link arm. The annulus should be fixed, and that is fixed. We've got a positive 1, a negative 1. Yes, the overall annulus is fixed, which it is. It's not rotating at all. Adding up the planet column, we've got the positive 1 minus the 3.33 recurring, so negative 2 1/3 effectively there. And then adding up the sum, we got the 1, and we're adding 2.5 to get 3.5. So with the solution here, we've straight away can see the gear ratio between the sun and the link arm, which we were asked for, and that's going to be 3.5 to 1. So 3.5 on the sun wheel and 1 on the link arm. 3.5 to 1 is the gear ratio. Okay, so that's a little exercise showing how to calculate the gear ratio using the tabular method. Now we're asked in the question, this is something we're going to work through together, to calculate the gear ratio between the annulus and the link arm. So that's the exercise we're going to do together. I've got this over the page here. Okay, so I want you to fill this in with me as we go through the process for this particular gear train, all right? The sun is now the fixed gear, and in the previous situation the annulus was fixed, but the sun is fixed now. Okay, so going through our process, same thing for the first step. We'll assume all the gears are locked, and we apply the positive 1 rotation for everything, so everything gets a positive 1 in that first row, so positive 1. Let's think of the second row. We've got, in this case, the sun is fixed, so if we fix our link arm, we're going to rotate the sun negative 1 revolutions. Because the sun actually is fixing the gear train this time, so that's the one we're going to sort of cancel out the positive 1 with that negative 1 here. So for the link arm, we're assuming the link arm is fixed here, so that won't rotate in this particular row. Then we've got to work out the velocity ratios for the speed of gear A over the speed of the sun gear in this case. So the speed of gear A divided by the speed of gear S. So that would be, in this case, the number of teeth on the sun, the gear S, over the number of teeth on the annulus, the gear A. Now we will have to put a negative in this situation because the sun and the annulus go in different directions. Okay, so I've got a negative there. And what we're effectively doing in this box is just really transposing to find the speed of the annulus. All right, so I'll put the figures in here. So 40 teeth on the sun gear and 100 teeth on the annulus. Okay, so that gives me double negatives. So that's going to be positive 0.4. Now for the next one, we're looking now for the planet to the sun in this case. Again, the sun is moving -1, so I'll just put the figures in this case. So -1, and that's multiplied by sun, isn't it? The sun's 40 again, 40. But this time it's divided by the 30 for the teeth on the planet. So think of the sun and the planet, they're going to go in different senses, aren't they? So a negative I need there, so that will give me a positive again down here of 1 1/3. 1.3 recurring. And of course the sun is going -1. We said -1 in the left hand side, so -1 over here. And then we just total up the columns now. Let's total them up, see what we get when we add them up. Okay, I'm just going to go to I've got a slide where I've written it out more clearly to follow there. That's my slide, a bit more clear if you see that slide there. So in this case, if we want to find the gear ratio between the annulus and the link arm, I think that's what the question wants us to do here, then we can see between annulus and link arm it's 1.4. Gear ratio between the annulus and link arm, shown for a table, that's 1.4 in there. And that's with the sun wheel fixed. Okay, so you can see you get different velocity ratios by fixing different items of the epicyclic gear train. Okay, I'm going to take you through an exercise now. We're going to do this exercise together here. So these are very difficult and they will with some practice, but you'll get plenty of practice. So in exercise 1, we've got an epicyclic gear train, form shown in the sketch. Now the annulus in this case is 57 teeth, so this annulus thing here, 57 teeth. And the sun wheel is 19 teeth, so the sun is here, sun wheel, and that's 19 teeth, all right? So what it wants us to find here, first part is, it says determine the number of teeth required for the planet wheel, so I think of the geometrical consideration there. Second part, we've got to find the gear ratio between the sun and the link arm if the annulus is fixed, so very similar to the previous question, but it's a bit. And then finally, we've got to find the gear ratio between the annulus and the link arm if the sun is fixed. Okay, so different configurations. So I'll try and take you through the first parts A and B, and then hopefully you have a go at part C on your own then. Okay, let's start looking at the geometry then. Reading from the question, we know that the annulus had 57 teeth, so just take information from the question here. We know that the sun wheel had 19 teeth, so it's 19 teeth. And we need to be careful that the annulus is going to be fixed in our first analysis. So again, as we said in the previous example, we can generate an equation, a geometrical equation. So from our geometrical constraints for the gears, again we can see that the diameter of the sun plus twice the diameter of the planets is equal to the diameter, the pitch circle diameter of the annulus, so that's no different as before. And again, I'm writing that straight away in terms of number of teeth. So rearranging the equation, number of teeth on the planet, I get 19 teeth, if you want to just check the figures there. Okay, so part A was to find the number of teeth. This is actually now part B we're looking for, so it's part A and B effectively. So part A and part B really. Part A was finding the number of teeth, part B, now we're going to find the velocity ratio. We're asked to find it for the sun and link arm with the annulus being fixed here. So again, because we've got a fixed gear, we can apply the +1 technique across the board. Assumption made that all the gears are locked, and we're going to give one revolution about the main axis, so all the gears go +1. Next line. In this case, we know the annulus is fixed, so the annulus will get our -1 revolution in this case, because it's got to be fixed overall. We've got a +1 in the first row, so -1 in the second row will cancel out to give 0 in the third row. It's what we want, it is fixed. And of course, we have to always make sure we fix in the link arm in the second row because everything is relative to the link arm. So we're going to fix the link arm and we're going to apply an annulus rotation of -1 revolutions. Start to fill in the table. And then just simply add up the columns to get the final row. So if we want to find the gear ratio between the sun and the link arm, which we're looking for, so the sun, it says in the table, is 4, link arm is 1, so the gear ratio is 4 to 1. And the gear ratio between the planets and the link arm, if I want that one, then that's -2 to 1. So that's -2 to 1, again from the table above. So that's part B. There's a better solution there. Okay, a bit clearer to see when I write it in text. Now what I would like you to do is to have a go at part C. So part C, the gear ratio between the annulus and the link arm with the sun being fixed. So this is with the sun being fixed. So when the sun is fixed, the gear ratio between the annulus and the link arm, I think that's what the question wanted us to find. It's 1 1/3 from the table above. It's a positive sense. To exercise 2E, an epicyclic gear train of the form shown in the sketch. Now shaft A is rotating at 600 RPM. So shaft A, this shaft here, that's rotating at 600 RPM. And that's in a clockwise direction, we're told. While the annulus D rotates at 300 RPM. Now, straight away I can suggest they're not going to fix anything here. They've given us 2 velocities initially. They've not fixed anything. Everything must be free to move, I think, here. So it's D rotates 300 RPM, and that's anti-clockwise. We've got to calculate all unknown gear teeth. That might be a challenge in a moment. And the angular speed of the shaft connected to link arm F. So angular speed of this shaft here is what we're trying to find. We're given in the question some information. We're given that wheels A, B, and have 40 teeth, 25 teeth, and 80 teeth respectively. And gears B and C rotate together, so they're compound gears then for B and C. All gears have the same module. So nothing's fixed here in this case, so we need a slightly more complicated approach here. That's the information from the question. So the first thing we're going to have to try and do is find in part A effectively, is to find all the unknown gear teeth. So we've only got A, B, and D given to us, so we've got to find C and E here. So let's see what we can do with that one. Okay, got this geometry here. I've added this sketch to the right hand side. Let's see if this helps with the understanding. So the first thing to do, as always, is get the information out of the question. So from the geometrical constraints then, we've got, so let's look at the information we got. So the diameter of gear A added to twice the diameter of gear B, which is the planet gear, there's 2 planets, must be equal to the diameter of gear E. Alright, so that looks okay. So diameter of gear A added to twice the diameter of gear B, the planets, is equal to diameter of gear E. That's okay. That's what we had before, and I can see that's applicable from this train here. Okay, that's no different than it was before. I'm going to write that in terms of number of teeth though, so again I can rearrange. So that's no different as we had in the previous example, that approach there, very similar approach there. Just rearrangement slightly different. We're finding gear E in this case. Okay, so equation 1, we had equation 1 before. Now we have to find the number of teeth on gear C. It's a bit more complicated, this one. X is across to the next gear, so that would be down to, I'll draw that in here just to clarify. So we've got the diameter of gear D minus the diameter of gear C, so that would be correct. So diameter of gear D would be across so from here to here. That would be gear D. What we're doing is we're taking off half of C there, and we're taking off half of C here to get to the diameter X. So that looks like it makes sense to me. Diameter of gear D is across here, and then subtract diameter of gear C, that gives us X. That looks okay. And that's equal to the diameter of gear A added to the diameter of gear B. Let's check that one out. So that would be diameter of gear A And then, yeah, that would be okay again. When it's the diameter of gear A added to, we've got this sort of half of B there, and then half of B here. That would be okay as well. We can write that to as number of teeth as always, so ND minus NC is equal to NA plus NB. We know all the number of teeth except for on gear C, so we can transpose the equation. So we want to rearrange it so you could add NC to both sides if you want to, and then subtract NA, subtract NB. We want to do it. So NC is equal to ND minus NB minus NA. Put the numbers into that, I get 15 teeth. Exercise 2E continued here. Just extracted all the information from the question and also stated the calculated gear teeth on gear C and E. Note in this case that no gear is fixed, so we're going to apply the procedure where we lock all the gears and all gears are then given a positive M revolution. So in our step 1 of our table, every gear gets a positive M revolution across the first line here. And in step 2 of a table, we're going to fix a link arm as always. The link arm is F in this case, shown here. And we're going to rotate gear A, the annulus, by positive N revolutions. So now in step 2 I need to work out the velocity ratio calculations for each of the gears here, which I will do on the following slide where I have more space. Now let's consider step 2, and I'm going to consider step 2 on this slide to give myself just a bit more room to show the calculations, that's all. So we're going to have the link arm fixed and we're going to rotate gear with positive N revolutions. Just note that the choice of rotating the annulus is arbitrary because we could use any gear to be rotated positive N revolutions here. So let's consider the gear ratio for gears B to A. In other words, the speed of gear B and C, because don't forget B and C are compound gears on the same shaft, with the speed of gear A. So to work out the gear ratio for this simple train, A to C, it will simply be the NA divided by the NB multiplied by the speed of gear A, which is told as N in this case. Notice the negative have been added here. If we consider the respective rotations, if we say gear A is positive, then of course gear B must be going negative, so that's why I need the negative added to the equation here. Just inserting a number of teeth, that becomes 40 for NA divided by 25 for NB, so calculating I get negative 1.6 N revolutions. So that's the ratio of gear B to gear A. Next, let's consider the gear ratio of D to A. So this is the speed of the annulus, gear D, relative to the speed of the sun, gear A. So our gear train here will be A to B, B to C are compound gears, and then C to D. So I have a compound gear train here. So looking at the gear ratios, we have the number of teeth on gear A divided by the number of teeth on gear B. That's for this simple train. And we multiply that by the number of teeth on gear C, multiplied by the number of teeth on gear D, and that's for this simple train. What you actually have there is our formula we used in the previous lecture relating to the product of number of teeth on the driving gears divided by the product number of teeth on the driven gears, because in this case NA and NC are driving and NB and ND are driven. We multiply that by the speed of gear A, which is N. And once again, I've put a negative here because of the sense of the output gear to the input gear. And again, let's just check that through. If gear A is in a positive sense, then gear B will be in a negative sense. Gear C on the same shaft as B will be negative. And don't forget the internal teeth here at gear D will mean that also goes in a negative sense. So the output D rotation is opposite to the input sense of gear A rotation. Again, inserting the numbers, number of teeth on gear A is 40, on gear B is 25, gear C 15, gear D is 80. That evaluates to negative 0.3 N. And finally, we need to calculate the gear ratio of E to A, so speed of the annulus E relative to speed of the sun A. So our gear train now is A through B to E. Notice in this case though, it's a simple train and gear B is actually an idler gear because it's being driven by A, but gear B is driving E. So it's a driver and a driven, that makes it an idler gear. So we don't need to consider the number of teeth of gear B in our calculations. So again, evaluating, we'll have the speed of gear A multiplied by the number of teeth of gear A divided by the number of teeth of gear E. Again, if we think of the senses of the gears, I've got positive for A, that would be negative for B, and of course negative for internal teeth E. Hence the negative in the calculation here. Inserting the number of teeth, gear A is 40, gear E is 90. That evaluates to negative 0.444 revolutions. So there's our speeds that we'll now insert into the table for our calculations. And here are the ratios inserted into line 2 of our table for reference. Gear A positive n, gear B and C negative 1.6 n, gear D negative 0.3 n, gear E negative 0.44 n, and gear F, the link arm, is fixed. And of course then step 3, finally we summate the columns. So summating the column for the speed of the annulus, we get m plus n. Summating the columns for the speeds of gears B and C, we get m minus 1.6 n. Summating the column for the speed of gear D, we get m minus 0.3 n. For the column of speed of gear E, we get m minus 0.44 n. And finally, for the speed of gear F, the link arm, we get positive m. From row 3 of our table, we can now generate appropriate simultaneous equations related to the speeds we're given in the question. The speed of gear A, that was 600, so I'm taking this equation. So speed of gear A is equal to the m plus n. That's where the 600 equals to m plus n comes from. I call that equation 1. I'm also taking the speed of gear D, which was given in the question. That would be negative 300 because of the sense given in the question. It's going anti-clockwise, whereas the 600 goes clockwise, and that equates to the m minus 0.3 n here. I call that equation 2, just giving them handles, that's all. So I'm just going to solve these. It's actually quite easy to solve these because they've both got an m in the equation, so I can simply just subtract one equation from the other and they'll solve quite nicely here. So just equation 1 subtract equation 2, we'll be just literally subtracting the equation, so that's my 600 and I'm taking away from that the minus 300 there. That's equal to my n, subtracting the 0.3 n there. Okay, so the simultaneous equations there. So that gives me a value of n. If I rearrange the equation, this equation here, so I'm going to get 900 on the left-hand side divided by 1.3 on the right-hand side. So that's where this equation is coming from. All right, so the n is equal to 900 divided by 1.3. That's 900 there. That's 1.3 n there. So n is 900 divided by 1.3. That gives me 692.3 RPM. And if I back substitute into any of the equations, so I'm just using simultaneous equations here, I'm back substituting any equation you want to choose, and I can work out the value of m in this case, which is negative 92.3. So again, the maths is telling me the senses here in this particular case. So the m would be negative 92.3. So in this particular question, they've asked us to the speed of shaft F. Well, it rotates at the negative 92.3 RPM. It goes in an anti-clockwise direction, in other words. And just for clarity of the solution, that m we just calculated from our simultaneous equation is this m in the third row of our table for the link arm F. That's the speed. So the speed of m is negative 92.3 RPM. In other words, anti-clockwise. So that's sort of the all singing, all dancing kind of question there, where you've got nothing fixed, but you are given these two speeds. But using those two speeds, you have to then work out the speeds from the equations that you generate. Okay, let's consider exercise 3E, which again we're going to solve using the tabular approach. In an epicyclic gear train in which wheel A has 20 teeth, so this is wheel A, the sun wheel here, and it rotates at 1200 RPM. It's got speed given. The fixed annular wheel The fixed annular wheel, C, has 120 teeth. So this is, and it's fixed in this case. I'm always pleased when I hear it fixed, because that will mean the solution sequence is slightly easier for you. Got a fixed gear. And the other annular wheel, wheel E in this case, there, has 100 teeth. And wheel D has 40 teeth. Wheel D is 40 teeth there. We've got to determine the speed of rotation of angular wheel E. It says note both the gear wheels B and D rotate together, so they're compound gears. B and D are on the same shaft in this case. Up to that stage, what you're going to do is go through it and find unknown teeth that might be missing on the analysis there. So you want to find the teeth on gear B, for example, and go through the velocity ratio approach with your table, work out your relationships, and answer the first part of the question to find the speed of gear wheel E. And then when it says about calculating the fixing torque, notice they give you a power that's supplied to gear wheel A. So we've got an input power. We're going to calculate the fixing torque required at C. So the approach we use for finding the fixing torque at C is basically that we outlined in the previous lecture when we were calculating holding down torques on our compound gear trains. As you know, the power at the input, an assumption you would make in this case is that the gearbox is 100% efficient. So if you know the power at the input, then you know the power at the output, and you can find the appropriate torque at the output. And from that, you can find the fixing or holding down torque required at C. So can I leave exercise 3E with you and let you have an attempt at that on your own? Don't worry if you get the wrong answers, just send me something through that I can engage with and I can give you feedback. Even if you only get part way through the solution, that's fine. Send it to me, let me have a look at it and I'll give you feedback on it. So take the process step at a time if you want to. All right, so I'm going to throw this over to you, but feel free to let me have a look at what you've done. Don't feel you've got to do the whole solution before I see anything. Do a bit of the solution and then can you check things out with me if you want to.